Okay, let's start the second talk today. It's my great pleasure to introduce Professor Ursula Ludwig from Université Paris-Orsay. She's going to talk about the width and deformation for singular spaces and radial Morse functions. Please.
So thank you, first of all, for the invitation to come here. So if you go to Singularity meetings, either you meet mathematicians from Sao Carlos, or you meet people who at some point have spent 1 year, 2 years here, or at least have come to these famous meetings. So at some point you become the only isolated singularity not to have come. And so I'm particularly grateful to come and participate in this meeting and celebrate Carmen's birthday, so happy birthday. And I have to say that all my expectations, who have been high, have been surpassed by this perfectly nice organized conference. So I will speak about the generalization of the Witten deformation to singular spaces and radial Morse functions. And so I started to think about generalization of what is called the Witten deformation in 2005-06, where I spent one postdoc year in France, shared between Marseille and Paris. And as you can guess, in Marseille I had the opportunity to work with Jean-Paul Bracelet. And so in my talk, some intersection homology as important invariant on isolated on singular spaces will appear. And then in Paris, my mentor was Jean-Michel Bismuth, and he is famous for several things, but he is in particular famous for what is called local index techniques. So this will be a talk situated in global analysis of singular spaces. And in global analysis, you are interested in giving comparison results between something topological, so topological invariance, and analytic invariance. So one famous result of the last century in global analysis on a smooth manifold is the famous Atiyah-Singer index theorem, which says topological index equal analytic index. So in this context, if you speak about analytic invariant, it always means that you solve some differential equation. So you need to know some techniques about differential or pseudo-differential operators. So if I'm speaking about analytic techniques in my talk, it will be meant in this sense, and not as you may mean when you say analytic type of a singularity, right? So analytic for me will always mean there is some differential equation in the background or some functional analytic argument. Okay, so I will start linearly in some sense, so I will explain each word in the title. And so the first part of my talk will to recall what the Witten deformation is in the classical situation, that means on a smooth compact manifold. And I will give a first definition of the Witten deformation, which is a very naive definition, as we will see later. But now let me just define the Witten deformation as just another proof of the famous Morse inequalities, but this time an analytic proof, and maybe not the proof you use to learn in a course on algebraic topology, for example, differential topology, for example. So if you have a smooth compact manifold and a smooth Morse function on it, then you have a relation between the critical points of the function, which is a local data of the function, and the global data of the manifold, which is a topological data and is usually encoded in the Betti numbers. So BIM will denote the Betti numbers, and CIF the number of critical points of the Morse function of index I. And then the Morse inequality state that the Betti numbers are a lower bound for the number of critical points in that index. So, and for experts in Morse theory, everything I'm saying holds for the strong version of the Morse inequalities as well, but for simplicity, I'm just writing this weaker version down. So let us see on the torus, you have here a maximum, so that is index 2 critical point because I have two unstable directions where I can descend. The minimum is I cannot descend further, so that means it has index 0, and then I have two saddle points which have one descending direction, so that are index 1 critical points. And of course, the only important Betti number for surfaces is the first Betti number, which is 2 times the number of holes. So here it's 2. And so you see that here you have even equality. So this is a perfect Morse function in this case, which is not always possible to have, but on orientable surfaces, yes. Okay, so now I will give you a proof which is different from the proof you would think of, namely an analytic proof. Of course, the topological way is to say that every time you pass a critical point, you attach a cell of that dimension. And so the manifold has a type of a CW complex built out of the critical points. That would be the topological argument. Now, I will explain Witten's argument, which is analytic. So its starting point has to be an analytic definition of the Betti numbers. So therefore, I denote by omega MD the RAM complex of smooth forms on the manifold. And I will need an extra structure, namely a Riemannian metric. On the manifold. So on one hand, with the Riemannian metric, I can always define the negative gradient vector field. But I can also use the Riemannian metric to induce a metric, which I denote by these brackets, on forms. So this is a so-called L2 metric on forms. So on these forms, this is an infinite dimensional space, but I have the L2 metric on it. So, and then with this L2 metric, I can define for the operator D its adjoint delta. So formally, it's just to say d alpha paired with beta is the same as alpha paired with delta beta. So if you think in terms of matrices, if D was a matrix, then delta would just be the transposed matrix, right? So, and then I can also define the so-called Laplacian. So this is, I take D plus delta. So if you take a matrix plus its transpose, it becomes a symmetric matrix. So I say in functional analytic terms, this is a self-adjoint operator, D plus delta. And now I do square it. D plus delta square will still be a functional analytic operator, a self-adjoint operator. Moreover, it is what we call a second order elliptic operator. Second order because I will derive twice, right? And so just by elliptic theory, this operator will have a discrete spectrum. So even if I'm working on an infinite dimensional space, I will look at the eigenvalues. So I look at forms which satisfy Laplace alpha equal lambda alpha for some lambda which will be a real number and which will be a non-negative number because here I have a square. So this operator is non-negative because of the square. So the most important eigenvalue is the eigenvalue 0. That means when I solve Laplace alpha equal to 0, those are the called harmonic forms. And so now I recall a classical theorem, which is the Hodge-de Rham theorem, which tells me the following. So the singular cohomology is isomorphic to the de Rham cohomology, which by definition is the cohomology of this de Rham complex, which I put up there. And moreover, so here in this first part, I have not yet used the metric. Now the metric comes in order to define the Laplacian. And so Hodge theorem tells you that every cohomology class can be represented by a harmonic form. So that means to now give the Betti number, I just have to count how many I forms I have which satisfy Laplace alpha equal to 0. That is an analytic way of defining the Betti numbers, if you wish. Okay, so this is just the starting point of the Witten deformation. I have not yet explained anything about the Witten deformation. So the Witten deformation will now be a deformation of everything which I put on this slide. So that means now I'm still on a compact smooth manifold with a Morse function and also a metric to be able to define the Laplacian, right? And so now I'm deforming the de-Rham complex. And I cannot deform the forms, but I can sure deform the differential d into a differential dt. T will be my deformation parameter. So, and in the way I am writing, I will be interested in particular when t becomes very big. So I will, in the end, look at the limit t goes to infinity. This I'm saying to you because Witten deformation is often written by semi-classical people, and semi-classical people look at the semi-classical limit, which is h goes to 0, and they use the parameter 1 divided by t. So if you look at the Witten deformation written by semi-classical people, they look at h goes to 0. So also let me say that if I take a negative parameter, t, so that means I just took the Morse function minus f, and with positive parameter. So therefore, it's enough to look at the positive parameter or non-negative parameter. So now I have not yet written down what is dt, what the deformation of d is. Now I give you the formula. So dt of a form alpha is made up like this. I take alpha and I multiply it with exponential tf. So here I use my Morse function. This is a function, right? The exponential tf is a function which I multiply to alpha. So this stays a I form, if alpha was a I form. Then I apply my operator d, and then I twist back by multiplying with e minus tf. And then I can use product rule to compute what I wrote here, and what comes out is d alpha plus t, the one form df, wedged to alpha. So you see this part also increases the degree by 1, because I wedged with a 1 form. So from the first definition, what you learn is, so you can easily see, now d square was 0, because the de-Rham complex was a complex. And so from the first formula, easily you compute dt square is 0. So you have deformed, but still you get a complex after deformation. So, and in the second way of writing, you see the deformation aspect, right? If t is 0, you have done nothing to your complex. And then you have associated a Witten Laplacian, which I can define as before, except that I'm working with dt. I have delta t, it's a joint, and then I take dt plus delta t squared. So, and now the first little proposition, I call it proposition 0 because it's not even in some sense a proposition, it's a remark, to see that that by deforming, I have not done harm to my situation. So first of all, also from this first writing, just the definition, in some sense, I defined dt like this, that I have an isomorphism of the undeformed to the deformed complex just by multiplying with e minus tf. So if you look at this formula in the right way, that really means that multiplication with e minus tf is compatible with taking differentials. So you really get here an isomorphism of complexes, which means that now this deformed complex still does compute your de-Rham cohomology or the singular cohomology. And then, moreover, you have a deformed version of the Hodge theorem. So what I wrote down, because of the isomorphism of complexes, singular cohomology, which is isomorphic to de-Rham cohomology, now that is the cohomology of the undeformed complex. Because of the isomorphism, it is also the cohomology of the deformed complex. And now I have a T-Hodge theorem. Now, this slide just is telling you that instead of working with de-Rham Hodge theorem, I work with deformed de-Rham Hodge theorem, and I don't lose any kind of information. I can do it equivalently to work with this deformed complex. So, however, what do I win right? I don't lose anything. These slides tell me I don't lose anything. But I do win something. Namely, this Laplacian, which is the famous Witten Laplacian, its spectrum is easier to study in some way than the original Laplace operator. You know that people studying spectral geometry on manifolds, sometimes they try to figure out the spectrum of the Laplacian, and it is hard. There are not many examples where you know the spectrum of the Laplacian on a manifold. Of course, you do know, for example, for a circle, you have the spectrum 0, 1, 4, 9, and all the squares, because the eigenfunctions are simply sin and cosinus k phi, right? So, and then k square is the eigenvalue. But, and for spheres in higher dimension, you can compute the spectrum explicitly as well. But in general, it's not hard. And even to give, for example, bounds on the first and second and so on, non-zero eigenvalues is not an easy problem. But now about the Witten Laplacian, I can say something about its spectrum. And this is the famous spectral gap theorem. So, already what we know is that this has discrete spectrum, so it only has eigenvalues, and they are non-negative, as I told you, because the operator was a square. This I know already. Now, the spectral gap tells you, in addition, that what happens with a spectrum is it decomposes into two parts. So I will have a part of the spectrum which lives here close to 0. So I will have sure the eigenvalue 0. How often? So eigenvalue 0 means that I solved Laplace t alpha equals 0. And that is precisely the Betti number, right? So the multiplicity of 0 is the Betti number. Then, moreover, I may have eigenvalues, but they are small. If my parameter t is big, I will have eigenvalues which are exponentially small and close to 0. Then I have this red zone where no eigenvalues appear, it's forbidden, and then I will have eigenvalues which tend to infinity, but they are at least of order t. So that means if t becomes very big, I have here a very, very big forbidden red zone. And so I have spectrum concentrating near 0 and a part going far away. So that means if I'm just interested in computing the Betti numbers, then just throw away this big part, because the only interesting thing is the 0 eigenvalue, so this one will be included in the small ones. Just look at the small ones now. This will be enough to compute the Betti numbers, right? So, and then it turns out that the eigenforms, which are eigenforms of the Witten Laplacian to small eigenvalues, they form a subcomplex. This is because the Witten Laplacian commutes with dt, just by definition. So I will denote with st dt the subcomplex of those forms which satisfy Laplace t alpha equal lambda alpha, with lambda being small, that means small here in this small interval around 0. So that is now a subcomplex, and it's finite dimensional, right? Because I'm looking just at these finite many small eigenvalues, and moreover, I can count how many solutions I have, and it's precisely given by the number of critical points of f in that index. So this theorem says, in some sense, that I do have a complex, this complex st dt, which I will call later the Witten complex. So I do have this Witten complex, which is in some sense generated by the critical points of the Morse function. And because of the proposition 0 I gave you before, it does compute the RAM, or singular cohomology, of the manifold. So I have produced a complex which is generated by the critical points and computes cohomology. That means out of this, I know that my Morse polynomial is bigger than the Poincaré polynomial. Or, simply said, out of this second part of the spectral gap theorem, immediately as a corollary, I deduce the Morse inequalities. Right? So I repeat, of course, here I made a count of the small eigenvalues, and so this is given by the number of critical points, and the eigenvalue precisely 0 is the Betti number, so it has to be smaller than CIF, and it was the Betti number, right? So, okay, so this is the spectral gap theorem, and as I as I wrote down already in the last slide, the idea of the Witten deformation goes back, of course, to Witten in a paper in Journal of Differential Geometry, which was called Morse-Urey and Supersymmetry. So you can see his motivation came from physics, and indeed, I mean, he is a physicist. And I will try to give you some idea behind the proof, and you will see why exactly a physicist may have an idea of proving Morse inequalities in this way, rather than the way we are used to do it. And then, so in the paper I mentioned, the explanation for the spectral gap, and then also for what I will recall later, the so-called comparison theorem, takes maybe 4 to 5 pages. But then the rigorous proofs are by Helfer and Sjöstrand, and that is around 80 pages maybe. And I mean, what takes so long is the harder part of the Witten deformation. I will come in a minute to that. This is what I call the easy part of the Witten deformation, which is just proving the Morse inequalities. So there is an anecdote behind, right? So Bott, you know his name, I mean, he worked with Morse-Urey. He proved, for example, Bott periodicity using Morse-Urey. And so he gave a school, it seems, in Italy about Morse-Urey, and it was a school for physicists. And there was someone asking questions all the time. And his name was Witten, right? And after, it seems, 8 months, Bott receives an email from Witten telling, oh, I finally understand your Morse inequalities. And so Bott was maybe first a little bit perplexed that it took so long time to understand them, but then I think he got rather fond of Witten's way of explaining Morse inequalities, because he mentions it in his paper, Morse-Urey Old and New, which is like a overview on Morse-Urey. So, okay, let me come to give you just an idea. I cannot give you the 80 pages of proof of Helfer and Sjöstrand, so I will give you an idea why this kind of spectral gap can happen when you do the Witten deformation. And I will do it in the situation where, say I have the simplest compact manifold you can imagine, which is the circle, with a Morse function, which is the height function, and I have the 2 critical points. So there are 2 parts in the proof of the Witten deformation, namely a local part and then a globalization argument. So underlying the Witten deformation is what we call a phenomenon of concentration of the eigenforms to small eigenvalues near the critical points of the Morse function. So therefore, in the very first part, you will just study a local model situation near the critical points. That means what I will do first is that I take this point, and I'm zooming in, and just looking at the small neighborhood and the model operator next to the critical point. So let's see. I identify the neighborhood of this minimum with the real line. Then I will use Morse lemma. By Morse lemma, the Morse function has a nice form, namely essentially x squared. So I put a factor just for my computation. It makes it easier. And then also I will assume that my metric was flat in this point. And then I can compute with the formula I gave you before. I can compute what the Witten Laplacian is. So now I have put here local to say that it's just a local model. I put the parameter t, which is the deformation parameter. I put plus because I'm in the minimum. And I put I to say that I am on I forms, right? So I will have a formula for functions and for one form, so which looks a little bit different. So, okay, so let's look at the formula. You see the first term here, it's just deriving twice. And of course, I put the minus sign because this is the geometric way. But this is just the usual Laplacian, right, on the line. Right, so this is the Laplacian on the line. This second term here, t square x square, it is actually that I take the gradient of f, right, that is x, that is why I put here 1/2. I take the gradient and I take its norm, so I have here x square. And then I have a number operator. And see, if I had functions, then this is minus t. If I'm on one form, this is plus t. That's all, right? So, and now you see, if you have studied physics, I have done this, and in the second year of physics, I met this operator here, because it's the quantum harmonic oscillator. So, and then my exam in physics was, first question, write down the spectrum and eigenvalues of this operator. So every student in physics learns this, and the spectrum is just 1, 3, 5, 7, and so on, just the odd numbers. Because of this t here, it will be t, 3t, 5t, and so on. And now I have to cook it up with this minus t or plus t, right? So that means that what I get is that the spectrum of this local model is just the pair numbers times t. And moreover, if I'm looking at the eigenvalue 0, it can only happen, so when I had here the ground state, which had energy t, and when I is 0, then here I get a minus t, which compensates the t. So I can only get the eigenvalue 0 once, and this only on functions. And here I wrote you down the ground state, which is the kernel of this local model operator. And what you should see from this, you see this is exponential minus tx squared. T is very big, right? So I think of T being very big. So this is a Gaussian which concentrates more and more near my point P plus. So what you see here in the last two lines is a local version of the spectral gap theorem, because I have the eigenvalue 0 and then it goes on with 2t, right? So I have my order T gap. And then moreover, I see I have small eigenvalue, which here is precisely 0, only once. And in my model, I have only one critical point, right, which is the P plus. Of course, I can do the same thing with the point P minus, and then there are some signs to be changed. And what I get is that in the kernel lives the brother of my function. It is a Gaussian, but one form. Right, so dx makes it a one form. That's the only difference. But also I had now a maximum, that means index 1. So my small eigenvalue appears in degree 1 of the forms. Okay, and so this is the local argument, and you do have to globalize it. And in order to globalize, so it's harder, you have to write things down, but what is important is that here you have an exponential decay, because then if I multiply this with a cutoff function, I can see it as not a form living on the line, but on the circle in a small neighborhood. And I make an error, but this error is small. This is why in the global spectral gap theorem, you have not precisely eigenvalue 0, but eigenvalue which may be exponentially small. Now, I have to say that in the example of the circle, you will have precisely 0 in this case, because it's a perfect Morse function, but this is exceptional, right? In general, the eigenvalue, the zero-ness doesn't stay like this, but you get something small still. Okay, so this was the easy part of the Witten deformation. There is a harder part of the Witten deformation, which is what I call the comparison theorem between Witten and Thom-Smale complex. So in the situation when the pair consisting of the Morse function and the metric satisfies what is called the Morse-Smale condition. So this is a generic condition which you can always achieve by perturbing either the function or the metric. So it is a generic condition, but under this, oh, sorry. Oh, no, what has happened? All the secrets. Okay, so if you are in this more Smale situation, which is a generic situation, you can define what is called the Thom-Smale complex. This is a complex, again, generated by the critical points. It's a complex typically in homology, and what you are doing to define the boundary operator is that you count trajectories of the negative gradient flow between critical points of index difference 1. I will explain it on the torus so that you go home with another way of computing the homology of the torus if you want that. So now you see this picture of the torus. I changed it compared to the first slide, because the first slide, the more Smale condition was not satisfied. So I have to wiggle the torus a little bit to get more Smale condition. More Smale in this example is just that I break up the trajectory between the two saddle points. Okay, and so then, for example, to define boundary of the point here, of the maximum, I have to count all trajectories going from the maximum directly to the two saddle points. If I'm looking at the trajectories going from here to this saddle point, I have two trajectories, one in front and one which goes behind. So I should say 2 as boundary, 2 times this point. But because the trajectories, if you orient it and so on, they come with opposite signs. So actually, it's 1 minus 1, and so it's 0. So you see, and this will happen for every count. So here the boundary operator is 0. If you count every time, I have 2 trajectories, but with opposite signs. And then, of course, this complex computes the homology of the torus. So, and a hard part of the Witten deformation tells you that in the limit, the Witten complex does to converge, I have to say, to the dual Thom-Smale complex, because, as I told you, the Thom-Smale complex is usually a homological complex, right? So and the Witten complex is cohomological. So this has been proved by Helfer and Sjöstrand using semi-classical analysis. And there is a second proof of Bismuth and Zhang, which is a little bit different, and it's based on a result of Lodenbach on the closure on unstable cells. So I'm citing this result also because the title of the paper of Bismuth and Zhang is Ziegler-Müller type theorem. So their goal is not to give another proof, but really to use the Witten deformation in order to prove comparison result of torsion, analytic and topological torsion on manifolds. And their result is the most general result possible to have, and it uses the Witten deformation as one essential ingredient. So some literature, I have mentioned already some names. Of course, Witten deformation has a large development, and I cannot cite all names. But just let me mention, there is a holomorphic version of the Morse inequalities due to Demailly, and this one is like a standard tool in complex analysis. If I go to the seminar in Paris on complex analysis, nearly every time the speaker says at some point, now I'm using holomorphic Morse inequalities, right? So. And also recently I learned in geometric quantization, sometimes it's also used. So the list will continue. So what I want to say is that the Witten deformation is not only that you give another proof of the Morse inequalities, it wouldn't be so famous, right? Because you go to the nice book of Milner and you have a nice proof of the Morse inequalities in a couple of pages. But the fact that you are willing to read 80 pages of proof is that really is a method which is very useful in many different situations. And also I have not mentioned in Fleur homology has been completely inspired by Witten. So the Fleur homology in some sense is the baby model is the Thom-Smale complex. So in Fleur homology, they call it Thom-Smale-Witten complex because they learned it through Witten and not the original papers of Thom and Smale, which are in the 50s, 60s. And there's also a nice anecdote. I mean, the Thom-Smale complex, you can find it in a paper of Thom in Cras, not au compte rendu. But he missed the transversality condition, it seems, and Smale fixed that. And it's very paradoxical that he would not think about the transversality condition the right way. But I mean, okay, so I have dealt in the last years, as I told you, with trying to generalize this method to singular spaces. And the singular spaces I'm looking at are what I call singular spaces with cone-like singularities. So that means you see that here I denote by X my space, but I also have G, my metric, my Riemannian metric. This is important in my context. And so this space, I just for simplicity assume I have only one singular point. And so my space outside my singularity, it will just be a compact manifold with boundary. And then near the singularity, I have a conic structure, as all of you are used to. But what is now maybe different with what you are thinking of is that this conic structure is conic also in the metric sense. So, of course, if you think of algebraic complex varieties, we know by examples of Birbreyer and Fernandez and work of Birbreyer, Neumann, Pichon, for example, already on normal surfaces, this is a rare thing to have, right? But if you are doing a global analysis program, as I am doing, you need to study differential operators on a singular space. And the analysis for the cone-like spaces is very involved, while for algebraic varieties, there is much work left to do, I think. So therefore, if you are doing a global analysis program, cone-like singularities are a natural singularity. And so for an algebraic geometry, a natural singularity is something else, of course, right? So, okay, so what do we know? Let us look again at the smooth proof and what we threw in our pot to cook up the Witten deformation. You had the RAM, so the duality between singular and the RAM cohomology. You have Hodge theory, of course you have Morse functions, and actually you don't use the Morse function, you rather use the negative gradient vector field. So in some sense that is the important thing. And then if you look at singular spaces, some version of this theory we have for singular spaces. Of course, we know by Jean-Paul Stock that intersection homology is the important invariant, topological invariant for singular spaces. So it appeared late, so 77 you told us, so it is, I wrote here 80s, but a little bit earlier, Goretzky McPherson worked on intersection homology, and then at the same time, Chigger was working on cone-like singularities, defining what is called L2 cohomology. And then Sullivan pointed out, oh, but the local calculation, which we have seen in the school part, so it is the same for both. So actually there is a duality between these two. And then you have a L2 Hodge theorem. You also have famously stratified Morse theory developed by Goretzky McPherson in order to understand intersection homology. But then as well, you do have another tool which is now classical in singularity theory, which are radial vector fields, which have first been introduced by Marie-Hélène Schwartz. And so let us keep this in mind. I will just give some more details on L2 cohomology, right? So this next slide will recall L2 cohomology. So now instead of looking at my de Rham complex of forms, I'm looking at forms. So I denote this complex with CD max. So I'm looking at forms omega, which are L2 integrable. So I had a Riemannian metric, so that means that I can define a L2 metric, so this makes sense. And also d omega is L2. So because of this second condition, I get a complex. So of course, I will say this is a Hilbert complex, and I take the maximal extension of D, which is a closed operator. So this is, because I'm doing functional analysis, so to be precise, I write D max. I could also have taken the minimal extension, for example. And then you have an associated Laplacian. So now I decorate again because, as I told you, so cone-like singularities, they are compact, but they are incomplete. And so this causes analytic trouble. So therefore I write this down in a correct manner and I have to put some decoration. But so I have a way of defining the Laplacian still. And then now my Hodge de Rham theorem becomes a Chigor-Goretzky-McPherson theorem, telling me there is a duality between intersection homology. So my intersection homology is always with real coefficients, and here my perversity is the middle lower one. So that is in duality with the L2 forms. And so this is L2 cohomology, and then I do have a L2 version of the Hodge theorem. But it is less innocent, because I really have to take care of which Laplacian I take here. So this is just a warning, which we will keep in mind. So as I have announced, global analysis on singular spaces with cone-like singularities has a rich tradition, which started with Jigger, and then there are several people, even schools you would say, who really put in place the tools you need to study differential operators on cone-like singularities. I will mention Melrose, Schulze, and their schools. I use mainly Brüning-Silly and Brüning-Lesch techniques. And then you have more recent development. So Alben, Leichner, Matteo, and Piazza, they have studied iteration of cones. And so they introduce what they call mezzo-perversity, which are perversities in an analytic way, which are perversities which live between the middle lower and middle upper perversity. And then together with Banagel, they give a sheaf version. So this is very recent result of, I think last year it appeared in arXiv. So then you have Gilles Kreiner-Mendoza, who have extended things on spaces with only one stratum, but not an isolated one. And I also want to mention Wertmann and Hartmann-Sprachwijk, who I think work here, who worked on studying analytic torsion on cone-like spaces. So this is really an active field of research. Okay, so now come back to Witten deformation. There are two ideas if you want to do it on a singular space, right? So the first is what to deform, and the second, how to deform it. So what I think that I pushed you in the direction to think L2 forms should be deformed and not the de Rham complex. And then, hopefully, because of the Jigger-Goreski-McPherson theorem, I would then get Morse inequalities for intersection homology, right? And then, how to deform? Of course, you would first think of stratified Morse functions in the sense of Goreski-McPherson. This is how I started, but it will not be what I will talk today. I will talk today about radial Morse functions, which are in some sense inspired by radial vector fields, which, as I told you, have been introduced by Marie-Hélène Schwartz, but I think many of you use them nowadays. So here comes the definition of a radial Morse function. So of course, look, this is my singular space as before, and a good Morse function, of course, it should be smooth Morse function outside the singularity. And in the singularity, I ask for this easy form. R is my radial coordinate, and I ask the function near this point to be like minus r squared, essentially. So now you see the picture is that the singularity is up. This minus sign means that I have a local maximum for the singularity. But I work with r squared. I could have worked with r. Topologically, it's the same, but analytic, not at all. So. And then, of course, I will get a deformed complex in the same way as before, and I will have a deformed Laplacian, again, in the similar way as I defined it slowly in the smooth situation, right? So, and then, so now I come back to proposition 0, but the singular version of it. That is to say that the Jigger-Goreski-McPherson theorem doesn't suffer under deformation, right? So here I put down that even under deformation, I compute still the intersection. Here I missed the middle-lower perversity, right? So, but this proposition is really a proposition, not only a remark, because of this thing. It's a technical thing which you have to deal with. So the domain doesn't jump. So for example, when you use stratified Morse functions, the domain would jump typically. So here I have no jump, and so this you have to prove, right? So that there is no jump. Okay, and if we believe, or if we hope that Witten... No, it just says that the domain is the same. It is the same, yes. So omega in the domain of the Laplacian is equal to omega in the, yeah. Okay, so if we hope that the Witten deformation does go through for singular spaces, then the first thing we will check is the first step in the proof, which is to give the local model. And so the local model at all the other critical points in the smooth part I know already from the smooth theory. So just look at the local model at the infinite cone. So to treat a situation near the singularity. And so here is the local model situation. I have my cone-like metric here. I have my radial Morse function. And then I can compute the local operator, which has a very nice form. So here I have my undeformed Laplacian, and then comes a number operator depending on the degree of forms. And then I have this t square r square as before, if you want. So in some sense, what happens is that I get a harmonic oscillator, but in polar coordinates. And I can apply what is called the Cheeger separation of variables to compute. So first of all, to see this operator has discrete spectrum and has a gap in its spectrum, and I can explicitly compute the kernel. So remember, in the kernel of the model operator, I had only one form in the smooth situation. So here, I do have, the kernel is 0 if the degree was small, and if the degree is big, I have something, so now this thing is important, is here, H is a form on the link, which is harmonic on the link. That is one thing which is important. And here you see the Gaussian factor in R square. So the Gaussian factor will tell me, oh, very good, I will be able to push it to globalize the argument. Of course, I have to work a little bit, but still, I'm hopeful. And this tells me that indeed what I get back is the local calculation for intersection homology, but the relative one. Because I had here minus r square, I could play the same game with plus r square, I would get the local calculation of the cone. I could as well, so here I work with D max, that gives me the lower perversity, middle perversity. If I work with D min, I get the upper middle perversity. And actually, in this local model, I can produce all mezzo perversities in the sense of Albin, Leichnam, Matteo, and Piazza, because it's such an explicit calculation. So, okay, and then I will be able to globalize and get the spectral gap theorem. But now this time, the only difference is my count of critical points will take into account the critical points in the smooth part plus the relative intersection homology of the singularity. And so, as a corollary, of course, I get the Morse inequalities for the intersection Betty numbers. Also, it is possible to generalize the hard part of the Witten deformation. And then you have, of course, to say what is this geometric complex. So there is the work to do because there is no Thom-Smale complex yet. So this I had to figure out. And then also you have to refine the analysis. So this is harder also for the analysis. And let me also say, finally, that at least the analytic part, so the spectral gap theorem, you can in some sense generalize to several strata with conditions on the function and the metric. And so accordingly, you get Morse inequalities as well. So for the bibliography, this is work which is due to appear, hopefully will appear in Krell soon. And, but there is an announcement or a short version in Compte Rendu where you can find it. And oh, sorry, excuse me. Yes. So, yeah. So what I need is this product normal form near critical points to be able to have a product situation. And so I will treat in the local model the product situation. I need also that the metric is locally product. This cannot be achieved along a stratum. So I'm working with metric which are adapted in the sense of Albin, Leichnam, Piazza, and Matteo, because, and the space has to be Witt. That is important, because what I need is that the domain doesn't jump. So there enters this result of Albin and Cossers. And I need the bounds on the derivatives as well, right? So, and then you get in a similar way where you have a shift, of course, here in the contribution coming from the index in the stratum itself. Yes, excuse me, yeah, so where this is, yes, excuse me, yeah. Okay, so, and then there has been also work by Alvarez Lopez and Calasa, who appeared, I mean, between the submission and the acceptance of my paper, but they are only doing the analytic part. So they only look at the spectral gap theorem, they don't go into the comparison theorem, and also their proof is somehow a little bit different from mine. But they also investigated kind of Witten deformation along strata with a similar condition as I am doing. So, okay, this it is. Thank you.
Are there any questions?
I have several questions. First, let's say, you have the deformation, the Witten deformation, and then you turn the time to infinity, right? And then you have some complex. Do you have any interpretation of this complex? Geometric, whatever?
Yes, so this is the comparison theorem I gave you. Yes, so the comparison theorem tells you that you have, so the geometric complex underlying is a complex generated by the critical points, obviously, in the smooth part, and the harmonic forms on the link. And then, yes, but then this is obvious because the Witten deformation tells you that should come out, but you have to say then the boundary how it is. But, so you have to write that down. And in some sense, it isn't, how to say, so if you look, there is a Morse-Bott complex, which is typically generated by, if you have isolated critical points, and all the forms of the critical manifolds. So, but it's all the form, that means it's infinite dimensional, right? So, but in some sense, you see I'm close to that kind of situation in some sense, but I produce a finite dimensional complex still, right? Because I'm just using the right harmonic forms. But
second, I think, you know, that if you work with all these metric structure that you use, you should basically take a metric just from the triangulation. If you make the quantification, then just definitely have it from the triangulation.
Yeah.
But let's work with the usual induced. You have a single set, right?
Yes.
Then you have a metric which is induced from the embedding.
Yes.
Then you have a natural Riemannian metric.
yes, that will be hard. I mean, that will be hard even for the isolated case. So for complex algebraic curves, I've done it. Everything works. I can write down the weak and the hard part of the Witten deformation for algebraic curves, but because their metric is nearly conic, right? The induced metric. But already for for normal surfaces, as you well know, right? Even the by Lipschitz classification says it's not conic, right? So and you don't have the analytic tools. That's the problem. I mean, even Goreski-McPherson's Chigor-Goreski-McPherson conjecture, so of course there is a proof of it by Yoshava, even for general, but I'm not sure if many people understand the proof. So if after so many years there is not clarity, that means it would be good to go and clarify these kind of things, even to be able, and I'm not only using that, I'm really using the notion of what is an elliptic conic operator, and so just the analysis is not so far for the analysis of differential operators for this kind of metrics is still in baby shoes. It has been, I think, the motivation in the field of L2 cohomology on singular spaces, but I think it's not as developed as you would wish to go further, right?
I would suggest to try from just real two-dimensional surfaces to see what it will give.
Yes. So, but as I told you, the complex curve case I've solved. Yeah.
Complex curve, I understand.
Yeah.
But let's start from the real surface.
Okay.
Then let's see what to catch in this direction.
Mm-hmm. Mm-hmm.
Finally, you say that you basically have the intersection homology, right?
Yes.
Thank you.
So, but I can tell you immediately, I mean, for the real surface, but with not necessarily a conic metric, you mean? Oh, okay. Mm-hmm. I see. Mm-hmm. Yeah.
The metrics that appear there.
Okay. Mm-hmm. I see. Mm-hmm. Thank you.
Okay. Any other questions? Okay.
The F. What happens if it's not a Morse function anymore, but something with isolated singularities?
You mean in the smooth part, or? So, as I told you, I mean, is a complex for Morse bot function, so you could probably adopt that, but. So, let me say, even the Witten deformation for Morse bot smooth thing has been treated by Bismuth, but it's harder in some sense. You will introduce at some point an additional parameter, so you can do it, but it's harder. So I have not looked into it in a singular context.
Just thinking that looking at something like an airy function, this Maslov index theory, could this be related in that kind of thing?
I don't know. I mean, I also know, I mean, for example, Braverman has looked into some degenerate situation as well. So, but I cannot say you exactly whether it applies to what you would say.
Thank you.
Thank you. Maybe last question. Okay, Terry.
I'm thinking about your last slide that you showed. If you have a complex variety with an isolated singularity, can you say anything about the contribution of the singularity?
So I think it will. So look, I'm not looking at these algebraic variety singularities because the problem is, as I told you, that I don't have the analysis for it. So if I will put my conic metric on this thing, it will be the relative.
I thought in your last slide you were talking about conditions that would allow you to say something.
Sorry?
I thought in your last slide you're talking about conditions that would allow you to say something. So
conditions on what? No.
Last slide. Okay, that's it. Yeah.
That's it.
So those are the four things you need. If you had those things, could you say something? Or?
Yes. So you get the Morse inequalities, and the contribution is the relative intersection homology again. But with a shift here coming from the index in the smooth stratum. Right? So this is what you would expect topologically. It's to say that in some sense it's not surprising, the Morse inequalities are not surprising because you could get them topologically if you wish. So that is not, in some sense, the result is not necessarily the Morse inequalities, but really to have the method at hand. Because if you are interested in Morse inequalities, you can do it with less pain in some sense, right? So there are other, I think even with Goreski-McPherson methods, they have this deformation lemma, which is not only for complex algebraic varieties, it's more general. So they could figure out the same Morse inequalities in some sense if they have radially growing function. So this is not you could, I think, more easily work with topological methods to get the right Morse inequalities. Yes. The goal is really to have the method at hand and try to push it further to other to applications to other problems somehow. Yes.
Let's thank the speaker.
Thank you.